So, welcome back. Today, I will talk to you about what is viscosity, which is due to the frictional forces offered by the various layers of liquids, and the Reynolds number, which describes whether the flow is streamlined, or it is turbulent, or it is in between. We'll talk about that. That is study of Reynolds. Now, most fluids do resist their flow all by themselves. This is an inbuilt property of fluids that they resist the flow. They're not ideal. This is just like the friction, which when two solids are in contact with each other, solids moving over solid surfaces, then they experience a kind of a friction. Why so? Because there is a relative motion between the layers of liquids. Now, for example, I take a case study where we enclose some oil, a very thin film of oil, between fixed lower plate of glass, this plate that I've shown here, and the upper parallel glass plate, which we are able to move with the velocity v over the layer of oil. Now, of course, we apply a force parallel to the lower plate. It's just like in the case of the modulus of rigidity that we offer, like you can see with a book, and we offer a force on the top of it, and then the pages they shift. So similarly, I've just shown you here, this is the oil which is enclosed between these two glass plates. We had initially, I'm just taking a small volume of the oil film, which is in contact between these two layers. It may be something like 0.1 to 0.5 millimeters in thickness. So it's very thin. The initial position is A, D, C, B. And when this force is applied here, then the position that is there becomes A, E, F, D. Okay, this position is obtained, and of course, between this point I'm taking here and this point, there is a shift of delta x, which is equal to the velocity times the delta t, the time for which it is being applied. I've shown you the velocity of the various layers, and when the force is applied tangentially, then the velocity over here in contact with the lower plate is equal to 0 because it is fixed, and the velocity in contact with the upper plate is v, that has been shown here. In between, the velocity drops down from v to 0, as has been shown by these arrowheads here. Okay, so now let us see what happens. The force that we applied tangentially, if we keep that force the same and we replace the oil by, say, honey, okay, then what we observe is that the velocity decreases for the same applied force which has been applied tangentially. So qualitatively we can say that honey is more viscous as compared to oil, that particular oil. And then we can categorize various materials if the viscosity is more or less for that. So we can just make a category of oils of different kinds, honey, grease, this, that, all kinds of fluids. Just here I write that the velocity of the layer in contact with the upper surface is V, and that with the bottom surface is equal to 0. Now, for any layer of liquid, there are two. If it is in between, for example here, then it has a layer here and it has a layer here, which has been shown over here. Okay, I show it that for this layer there are two forces which are acting, one in the forward direction and the other in the backward direction. Okay, the top layer applies the force Ft and the bottom layer applies the force Fb. Okay, which I have shown here over here symbolically. And because the fluid is still moving in this direction, therefore we say that this force in the forward direction is more than the force in the backward direction, which is the resisting force. Such a force between two plates of glass for this liquid, the flow is called a laminar flow, because the surfaces of the liquid, which we have different velocities, changing velocities, they act like lamina. So if the flow is through a cylindrical tube, shown over here, with an area of cross section A is equal to pi r square, and I've shown it here that this is the area of cross section, and the liquid is flowing away from us from this side to that side. What is interesting is that the velocity at the periphery of this tube is minimum, while the velocity at the center is maximum. In fact, what we can imagine is some tubes of flow instead of laminar flow in that case. Now, going back to where we started over here, where there was a force which was causing a shear to the liquid, when the plate was moving with the velocity v, and the shape A, B, C, D became A, E, F, D. Okay. When the force was applied to a certain area where the force was applied, then the stress becomes when the shape changes from ABCD to AEFD in time delta t. So if delta t is less, it will be less deshaping, and delta t is more, it will be more deshaping. So we can write then strain rate, shear strain rate, and that will turn out to be equal to delta x here, from here to here, divided by L delta t. Okay, delta x upon delta t is the velocity, so this will become V upon L. So for the shear case that we are dealing with, shear stress upon shear strain, that will yield what is called eta, which you call the coefficient of viscosity. So naturally substituting these terms, I'll get F upon A divided by V by L, or which we can say that FL VA, okay, and this is called the coefficient of viscosity. Well, the coefficient of viscosity, the unit is Poissels. Poissel, PL, okay. Another unit given to it is Newton second per meter square, okay. Also that we can say, because Newton meter square, meter minus 2, that is pascals. So pascals multiplied by this, so we get these set of things. And when we work out the dimensional formula, it turns out to be like this, okay. The coefficient of viscosity, eta, is different for different liquids. And one of the important factors that I must mention just now is that this is a function of this eta. It depends upon, it is a function of temperature. So if the temperature is changed, then naturally, because there is a molecular phenomena which is involved over here, the distance between molecules changes, and then the resistive activity also changes, and so there is a wide variation of eta with temperature, okay. Now I'll deal in the experiment to find out the value of eta. So we'll talk about the determination of eta, the coefficient of viscosity, by doing a very simple experiment where we have a metal block put on a film and of whatever fluid we are going to study, normally an oil, and in this arrangement I have a pulley and a string that goes over the pulley. The pulley is ideal. It is supposed to be massless and frictionless, etc. And this is a thin string which connects this block of a certain area of cross section which is in contact with the fluid, and to a weight which is hanging from here. In the present experiment, it has been taken as 0.01 kg. So this multiplied by the acceleration due to gravity over here will give us the force. Well, the velocity is the same here as well as here. So that the force of tension is the same all over the string, and this is equal to mg. The values we have taken, they can change, so it doesn't matter at all. You can see it, similar kind of an experimental details, etc. So what we find is that F is equal to T is equal to mg is equal to this is equal to this, 9.8 into 10 to the power of minus 2 newtons, and therefore the shear stress becomes equal to this force divided by the area of the film, 0.0, and then we find the strain rate, shear strain rate, which is equal to V upon L, where V is the velocity which has been found in meter per second, and this is 0.085 divided by thickness of the film, that is L, 0.3 into 10 to the power minus 3, and when we work out, we find out the value of theta, whatever, 3.45 into 10 to the power minus 3 Pascal second or parsecs. Okay, so we don't care about these things change, and you can find out the value of eta. Of course, whenever you express the value of eta for that particular liquid, do express the temperature at which it has been carried out, experimentally determined. Now, as I told you once upon a time, when I was being an advocate to Aristotle, okay, and I was saying that Aristotle was not as wrong as he was proved to be in the Galileo's days, and the people picked from there and they started criticizing Aristotle as it is. Now here we have a ball, a spherical shaped ball falling through a fluid. Maybe it is water, and for example it could be a fluid drop of water falling through the air. This is the force acting on this ball in the upward direction if the fluid density is sigma and the material density of the spherical shaped ball is rho, and A is the radius of that spherical shape, then we find that F is equal to 6 pi eta AV. Now this is an equation which has been obtained. It's not our endeavor right now to prove it and derive it, but we will remember it as, for application sakes, that the force which is applied on the ball in the direction opposite to the direction of motion of the ball through the fluid is 6 pi eta AV. Okay, so naturally it depends upon the eta, which is the property of the fluid. It also depends upon the radius of the ball under consideration, and so does it depend upon the velocity. And you can see it's just like a multiple variable system. Okay, so naturally if the drops are big, then the force is drop size is large, then the force that is obtained is larger. If the velocity is large, then the force also is larger. If A into V is large, then of course the value of F is large, etc. So we can plot F as a function of A into V on this side, and the force on this side. We get a graph like this, the slope of which will yield 6 pi eta, and from there we can calculate the value of eta. So anyway, there are many things which we can talk about. Now, when the ball is falling through the liquid, the ball has a volume of 4 by 3 pi a cube, and will have rho minus sigma into G, and this will be equal to this thing, which gives us the equation which defines the terminal velocity. The terminal velocity at the surface of the earth for a given fluid, of course, the things are G is constant, eta is constant, 9 is constant, 2 is constant, rho minus sigma is the constant. If the fluid and the solid or whatever is falling through that fluid, this is defined, well defined, then what we find is that this Vt, the terminal velocity, is naturally proportional to A square. Okay? So, when it is proportional to A square, then if I again make a plot of Vt with A square, I will again get a graph like this and can find out the value of this whatever is left over here, we can find there, and this is how we can explain. I can draw the graph. A square on this side, this is in meter square, and the terminal velocity, okay, then we get a graph like this. Slope of the graph will give you 2 rho minus sigma g upon 9 eta. So therefrom also, if we don't know the value of eta, we can calculate the value of eta if we have this kind of a relationship, study of this kind of a relationship. So very interesting about the Stokes law. Okay, and now we discuss next is what is Reynolds number. So Reynolds number, which was given by Osborne Reynolds 1842 to 1912, and he studied the flow of fluids, laminar or streamlined turbulent flow, and he derived an equation which is given by a number Re is equal to rho Vd upon eta, where rho is the density of the fluid, d is the dimension of the pipe, and eta is, of course, the coefficient of viscosity. We will again not derive this equation. Re is a dimensionless number. A dimensionless number, and you change the system of units and the value of Re will remain unchanged. It is independent of the system of units in which we discuss this thing. Now, what he found experimentally did show Osborne Reynolds that the flow is streamlined or laminar once the value is less than 1000. It can be calculated given all other things and the number can be obtained. It is turbulent. The flow, the motion of the fluid is turbulent when this is more than 2000. And in between, if the value of Re is more than 1000, less than 2000, then the flow is unsteady. Okay, it is neither streamlined nor we can say that this is turbulent. So it is just in between. Now this can be, Re is said to be equal to rho Vd upon eta. I can multiply by V here and in the denominator, and take this d out and put it here. So rho V square upon eta V upon d. And if I multiply it in numerator and denominator by the area, then this becomes equal to rho A V square and eta V A upon d. So this is the inertial force and this one is the viscous force. So it is the ratio of the inertial force and the viscous force. Let me tell you, friends, that the when the flow is low velocity flow, then it is either a streamline or laminar flow, and if the velocity increases, then of course it may become unsteady, turbulent, etc., etc. Friends, this turbulent motion, sometimes it is not desirable, but at other instances this is desirable. And the things are such that in the engineering designs of racing cars, of planes, of steamers and many other applications, we have to consider this Reynolds number, we have to calculate that, and we have to be careful about those things, because if we don't know the various properties associated with the fluids, we will not be able to negotiate the engineering and technology associated with the gadgets that we want to bring into use or application of those gadgets. So with that, we come to an end of today's lecture, and the next lecture we'll talk about the surface tension. Okay, we'll finish it off in one lecture: surface tension, surface energy, etc. Okay, then I again ask you question, we answer, and for now, for today, thank you very much.